Well, welcome again to the Darwin College Lecture Series, our third on the theme of beauty. 2 weeks ago, Robert May showed how mathematical beauty was a potent guide to discovery throughout science. And this week, we're turning to theoretical physics and the elusive world of quantum mechanics. And our title is, appropriately, Quantum Beauty. And we're very privileged to have as our speaker Frank Wilczek. He's a professor of physics at MIT. He studied maths at Chicago and Princeton. And he did his doctorate there before going on to Santa Barbara. He was winner of the Nobel Prize for Physics in 2004. And his achievements and originality in theoretical physics are, I think, legendary, not least in explaining the nature of the force between the quarks, around which our understanding of matter is currently based. He's also worked on the links between particle physics and the cosmos as a whole. And added to this, and much to many people's gratitude, he's also been a wonderful publicizer of science, his most recent book being The Lightness of Being. It's a pleasure and a privilege to introduce Frank Wilczek.
Thank you for braving this cold winter night. When I was asked, and thank you for that introduction, when I was asked to talk on quantum beauty, I was a little startled at first, because this is something that people rarely mention. But when I thought about it a little, it really caught my imagination, and that's why I'm here. Quantum beauty really is a wonderful, true thing to talk about. It, to me, is very special in that in the early history of science, people had visions that the fundamental laws of the world might be beautiful, might embody beautiful concepts. But it's really only in the quantum world that the ideal mathematical beauty shows up as being what underlies the real world. So this is where the real becomes the ideal. How does the world embody beautiful ideas? This is a question that people have thought about for a long time. I should say, I'm going to sneak up on quantum beauty by first putting it in historical context and trying to deliver on the idea that it's really the culmination of a long tradition of hope, desire, partial realizations, finally coming to full fruition. So Pythagoras and Plato intuited that the world should embody beautiful ideas. Newton and Maxwell, well, I should say, when I was thinking about this, I didn't explicitly think about delivering the lecture at Cambridge, but it turns out that I slid into it. Newton and Maxwell demonstrated how it could in specific impressive cases, but really it was only in the 20th century in modern physics, and especially in quantum physics, that we have a resounding yes as the answer to this question of whether the world embodies beautiful ideas. So let me start with Pythagoras. This is what Pythagoras looked like, according to Raphael. And he's writing there, you can't read it probably, he's writing down, all things are numbers, his famous credo. It's hard to know at this distance in time what exactly he had in mind, but we can reconstruct a little bit, I think. Pythagoras obviously was very impressed by Pythagoras' theorem. And what Pythagoras' theorem tells you is It's very familiar by now to most people, but is a startling idea if you think about it abstractly, tells you that geometry, the sizes and shapes of things, is really governed by numerical relationships, that numbers describe something very important about physical reality, sizes and shapes. So in particular, the Pythagorean theorem says that if you have a right-angled triangle and count the areas of these squares on the different sides, this number of squares here plus the number of squares here adds up to the number of squares there. Pythagoras, or his school, is also responsible for another startling, impressive realization along the idea that all things are numbers. Here's Pythagoras, according to the legend, demonstrating that if you have strings with weights that are in simple numerical proportions and or make their effective lengths have simple definite numerical proportions, be small ratios of whole numbers, then you get tones that sound harmonic, that are in good harmony with each other. So this was another amazing, startling relationship, still not properly understood really, between the world, here the world of perception of sound, that the harmony of sounds is related to numbers, namely harmonic sounds. Sounds that sound in tune are ones whose wavelength or frequency is described by what we call rational numbers, that is, numbers that have whole number ratios, especially with small whole numbers. This made a tremendous impression on Plato, and from that was transmitted down through the centuries. For further use, I wanted to, we'll see these coming up again and again, amazingly. Plato, among many other things, is famous for the Platonic solids. These are solids that can be made out of regular polygons, that is, polygons with equal sides and equal angles. So there are exactly 5 Platonic solids. One of the main results, and many people conjecture the reason that Euclid wrote his elements the way he did, was to culminate in the proof that there are 5 and exactly 5 solids of this kind. There's the tetrahedron, which has 4 sides, each of which is a regular triangle or equilateral triangle. A wonderful shape, the icosahedron, which has 20 equilateral triangles coming together in groups of 5. The dodecahedron, which will become our friend in this lecture, has 12 sides, all pentagonal. The octahedron and the cube, and that's all there is. There are exactly 5. And this was a very important realization that requirements of symmetry can pin down specific discrete choices for structure. And I think this inspired Plato very much. He tried to make the different elements, of which there were thought to be 4 at that time, out of these Platonic solids. One was left over. That was supposed to be the universe as a whole. I don't understand this theory in detail, but but the idea that there are exactly 5 things that you can use to construct the world was a remarkable kind of intuition. Plato also described a more philosophical theme that's been very influential and influenced our idea of how the physical world could embody beauty fundamentally, even though the appearance of things is messy and not manifestly beautiful in all its aspects. This was the idea, the metaphor of the cave, where we are all, as human beings, not seeing the true reality, but only a sort of projection of a deeper, richer reality. And one of our goals as thinkers, philosophers, or just appreciators of the world should try to be to imagine from these projections what the real thing is. And the real thing would be more perfect and more beautiful and more spacious more than the projection. But also, another important idea here, I think, is that there should be a precise mapping between the underlying reality and the projection. And that's how you could infer that your idea of what the underlying reality is actually corresponds to the universe. So those were sort of hopes and philosophical ideas for how beauty might be embodied in the physical world. These hopes and very partial insights became much more impressive when Cambridge started to get into the act. Here's one of my favorite diagrams, figures in the whole literature of science. This appears in Newton's Principia as the first figure. You have to imagine someone on top of a mountain throwing a stone harder and harder. And it's clear what should happen intuitively. The stone should go further and further. You can imagine the first few steps. Eventually, if you throw it hard enough, it goes very far. And eventually, if you throw it hard enough, it comes back and you complete an orbit. Okay? Then you can imagine a higher mountain. There would also be possible motions like this and this and this. And you see, from this, without any equations or elaborate mathematics, the idea that gravity could be a universal force, that the same thing could tell you that things are, how things move, projectiles move close to the surface of the Earth, and astronomical bodies orbiting around the Sun or the Earth. Also, the key idea of Newton's account of gravity and the system of the astronomy, that orbiting is really falling all the time. You're just falling and falling and falling. But because it's a moving target, so to speak, because you're moving, you never hit the surface. You just keep falling without actually getting closer to the ground. Newton also famously introduced the idea, or I shouldn't say introduced, but gave such an impressive example of the idea that it was firmly set forever, of the idea that the way to understand light in particular, but by an analogy, potentially everything in the physical world, was to break it down into its minutest components. Here you can break down white light into different colors, but then to show that these are the fundamental components, you have to show that you can use them to build back up the white light, which he did. Also that you can't further break down these components, which he showed in other beautiful experiments. This is what Newton looked like when he was making these discoveries as a young man. You see, he was very fit, also was very comfortable not wearing any clothes, and but most important, that the idea that the world was constructed according to precise constructions of a mathematical nature, that we should be ambitious in trying to find what those precise constructions are. And you can see his grim determination to do that. Moving on to Maxwell. These are Maxwell's equations, which systematized in the 1860s everything that was known about electrodynamics at that time, electricity and magnetism, plus one more thing, the entry in the box, which was Maxwell's original conception. He introduced this term, which says that changing electric fields produce magnetic fields, in words, because when he put together all the other equations to describe the phenomena that were known at the time, he found an inconsistency. So something had to change. In trying to think about what could change, he, I think, thought, well, we have this effect that changing magnetic fields produce electric fields. Wouldn't it be nice to balance the equation by having a kind of symmetric effect that changing electric fields produce magnetic fields? And he found that if he added this term, the equations became consistent. These equations to this day are the foundation of our understanding of the phenomena of electricity and magnetism and much else. Heinrich Hertz, the experimentalist who verified some of the surprising predictions of Maxwell's equations 25 years later, and invented radio. That's the way he invented radio, really, by looking for new solutions of Maxwell's equations, said this, which I find very beautiful and poetic and very true and very relevant. One cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them. What makes these Maxwell equations so special and made Hertz get so rhapsodic? Normally, if you look in the other writings of Hertz, he's normally very restrained and down to earth. Well, they have extremely powerful consequences, they have extremely pretty consequences, and they introduced a new idea of beauty into physics, the symmetry of equations. Let me say just a couple of words about each of those. The power. Here's Maxwell himself, a picture taken around the time of his discovery. When he added his new term to the equations, which remember said that changing electric fields can produce magnetic fields, we've already had the effect from Faraday that changing magnetic fields can produce electric fields. So now you have the possibility that you start with changing magnetic fields, they produce electric fields, which are also changing, they produce changing magnetic fields, and they keep going in a self-perpetuating, internally consistent kind of disturbance that can move through space. And Maxwell, with his equations, could calculate the speed with which these predicted disturbances would travel, and he discovered that it matched the speed of light. So Maxwell, being a very clever fellow, made the leap that we could scarcely avoid the inference that light consists in the transverse undulations, that's these wiggles, of the same medium which is the cause of electric and magnetic phenomena. And to this day, that's our theory of what light is. It's these disturbances in electric and magnetic fields. But there was much more, even much more than bringing the previously unrelated phenomena of optics into the study of electricity and magnetism. That is, that there are possibilities for disturbances of different wavelengths, different speed of changing electric into magnetic fields. The visible light corresponds to this band here, and that's all that was known at the time of Maxwell. But the equations had more solutions. Hertz eventually produced the radio waves, which have become famous as radio. And then there's infrared, microwaves are in there, ultraviolet, X-rays, gamma rays, all these things that are today hinges of modern technology and important parts of the understanding of the physical world were in Maxwell's equations that he guessed based on internal consistency and beauty and, of course, consistency with what was known at the time. These equations have, when you solve them, many beautiful features. I won't be able to do justice, of course, in a lecture like this to the beauty of essentially mathematical phenomena, but here's a beautiful thing that's very visual. This is the shadow of a razor blade or something with a sharp edge, a half plane. And you see that the shadow is not really a shadow. It's not the absence of light, but this was the formal division that geometric reasoning would have told you is the division between shadow and light, but some light goes over into the shadow, and this would continue if you could turn up the brightness sufficiently. And conversely, in the regions that are supposed to be perfectly light, there are bands of darkness. There's a lot of structure. It's a beautiful, very precisely calculable structure that you can get from the Maxwell equations that now can be compared directly with reality. So this hidden structure and light within darkness and vice versa, I find this very beautiful. It's just as concepts as well as just being sensually beautiful. You look at this thing and say, isn't that pretty? But perhaps most profoundly for the future of physics, Maxwell's equations introduced a new idea, an essentially new idea, which hadn't really featured into that time and has become more and more dominant in our attempts to guess new laws of nature. The idea that equations have symmetry, and the equations that nature likes especially have symmetry. What does that mean? Well, symmetry, of course, has loose metaphorical meanings in everyday life, but in mathematics, it has a very precise meaning. And the meaning I like to summarize as saying change without change. We say an object is symmetrical if we can make transformations on it that might have changed it, but in fact don't. So for instance, a circle is very symmetric because you can rotate it around, and that might have changed the circle into something else, but because it's a circle, it doesn't change if you rotate. A circle is especially symmetric. If you took an arbitrary shape and rotated it, you'd get something different. The same thing can be applied to equations. Here's a really baby example, but I knew this was a mixed audience, so I didn't want to press it too hard. So here's a nice equation, which you can see is very balanced between x and y. You'd be tempted to say it's symmetric, and by golly it is. If you change x into y and y into x, you get a different equation, namely instead of x equals y, it becomes y equals x, but it has exactly the same content. Whereas this equation is not symmetric. If you changed x into y and y into x, it'd be a different equation with different consequences. So symmetry is a property that certain equations have and other ones don't. Maxwell's equations, it turns out, have enormous symmetry. There are many, many transformations you can make on Maxwell's equations that would change an arbitrary set of equations, but don't change the content of Maxwell's equations. You can change electric fields into magnetic fields if you do it in the right way. You can change space into time if you do it in the right way. Things like this. And in fact, the study of these equations and their symmetry led to two profound developments that are at the heart of modern physics and will be at the heart of what I'm going to move on to, talking about the future. Special relativity, that is the boost symmetry, that you can make changes that mix up space and time and allow people to move by at a constant velocity. And the equations change. What's a magnetic field and what's an electric field and what's space and what's time changes. So they change in form, but their total consequences don't change. It's like x equals y becomes y equals x. And a less familiar kind of symmetry, gauge invariance, that's come to dominate modern fundamental physics. And the magic thing is, it also works the other way around. If you ask for equations that embody these two kinds of symmetries, you're led almost essentially uniquely to Maxwell's equations. Just as if you ask for the shape that's invariant under rotations, that has symmetry under all kinds of rotations, you're led to a circle or a sphere. So there's this perfect match between mathematical concepts of symmetry on the one hand and the equations that describe the world on the other. Okay, so now with that as background, let me move into quantum mechanics a little bit. Here we find Pythagoras vindicated. The mathematics of electrons and atoms is exactly the mathematics that's used to describe something like, a string vibrating. That's a little too simple, but more like a drum vibrating, or the vibrations of air in a woodwind instrument. They make patterns of standing waves, pressure and density that move back and forth. The musical instruments. In the case of quantum mechanics, the waves that vibrate are a little more abstract. They're waves of probability, and the things that oscillate one into the other are real and complex parts of wave functions. So that would take us far afield to really describe in detail, but the equations are exactly the same. So in the early days of quantum mechanics, when the physicists were developing these equations and trying to solve them, one of the main textbooks was Lord Rayleigh, another Cambridge guy's textbook called Theory of Sound, because the equations that were used to describe the generation of sound in musical instruments and the propagation of sound are so extremely similar to the equations of quantum mechanics. And if you look, for instance, at the simplest atom, the hydrogen atom, and ask what the electron wave pattern looks like that vibrates with a definite period, so ones that would produce pure tones, these are called the stationary states. These are two-dimensional sections of what they look like. Very pretty, very pleasing, described by very precise mathematical equations whose consequences have been checked to the 9th decimal place. The two-dimensional image doesn't do full justice to it. They have a lot of internal spatial structure. Here's one particular orbital and what it looks like. So inside your atoms, you have this wonderful structure going on that is also true, very precise, whose consequences we can check with fantastic detail. And we can use them to draw pretty pictures. Same concepts. The ideal meets the real. Time is limited, so I will not be able to do justice at all, even remotely, approximately, superficially, to the full beauty of quantum mechanics as it applies to the description of matter and the many phenomena of chemistry where beautiful solutions of the quantum mechanical equations arise. I'm just going to show a quick sampler of a particularly dramatic and relatively simple corner, the chemistry of pure carbon. So in a hydrogen atom, there's one proton and one electron, and the electron is bound to the proton and forms patterns that are centered on that proton. If you have many nuclei, many positive charges that can be attractive to electrons, the electrons are attracted to all of them, so they have to be efficient. They would like to spend their time a bit with all of them to play the field. And to do that in a maximally efficient way, to get the lowest energy, to have something that's stable technically, it's helpful to have things. I mean, if you find a good solution, you should use it over and over again. All the electrons are the same, all the nuclei are the same. So if you find a good solution, you should use it over and over again. And so that's the scheme, of course, that nature adopts. You form a regular arrangement, also called a crystal, and make orbitals. So the electrons move or concentrate their wave functions in the directions that point to the neighboring nuclei in a regular way. Carbon atoms have 4 electrons to dispose of. There are 2 especially symmetric ways of arranging those 4 electrons. One is to arrange 3 of them symmetrically, so they point to the vertices of an equilateral triangle. Okay, and so the orbitals are partly concentrated in the center, but then reach out, and they can also touch other carbon atoms at the points of this equilateral triangle. And then there's one left over, which you let wander off into a transverse plane. Another way to make it really nice is to have 4 of them, point them to the vertices of a regular tetrahedron, one of Plato's ideally symmetric arrangements. The Platonic solid with 4 vertices. And it's a wonderful thing that these are exactly arrangements that nature uses over and over again with exuberant flair. So I'll just show you pictures that will convey that, I hope convincingly. But there are equations that go with this. And I should say, one of the nice things about quantum beauty is the more you study it, the more beautiful it is. That's not always the case. So this is an arrangement in which you have these guys making the equilateral triangle kind of connections everywhere, over and over again. So each carbon makes equilateral triangles reaching out to 3 neighboring carbons, and the electrons are in these orbitals. This is a dodecahedron-like object, but a dodecahedron isn't quite flat enough. Okay, it would be too curved with the size of the orbitals to make it energetically favorable. So you can flesh out a dodecahedron with as many hexagons as you like, it turns out. So add to 12 pentagons as many hexagons as you like, then you can make a solid like that. And a particularly nice one that has many symmetries, additional symmetry, is called the buckyball, that has 60 carbon atoms, exactly 12 pentagons, and the rest hexagons. That was a great discovery that won the Nobel Prize for the discoverers. But it goes on. Here's a soot ball. These are soot. Really, the carbon is carbon. And in fact, these things are in soot. So hidden in soot are these beautiful molecules that, on closer study, reveal their existence. This is one that's been made with 800 carbon atoms, making a very impressive large sphere, and you can try to put things inside the sphere and move them around and have maybe practical applications. Here is the ultimate in the two-dimensional perfect symmetry, when you just have a two-dimensional plane that goes out forever with these equilateral triangle arrangements. Now it's perfectly flat. This is the substance called graphene that was only isolated in a pure form a few years ago, I believe 2003 or 4, and got the most recent Nobel Prize in physics. And you see, and I should say that theoretically, the properties of this material worked out in great detail already in the 1940s, because the symmetry of the equations and their definiteness allowed you to work out the physical consequences very precisely. And so once it was realized actually how to make it, progress in using it has been extremely rapid, and in understanding its properties. You can also take graphene and fold it over, or take a carbon sheet and make tubes out of it. These are called nanotubes. You can twist them a little bit before you reconnect, and each particular twisting arrangement has its own properties. These can be calculated from the equations of quantum mechanics. It's a lot of hexagons all put together, all with this threefold symmetric bonding. And there's a wonderful world of carbon with remarkable properties of strength and electrical properties that can be calculated from the equations and predicted. And then going to the three-dimensional arrangement where you reach out to the different vertices of a tetrahedron, that makes a diamond. And the reason diamonds are so hard is that this is an extremely efficient way to minimize the energy for electrons to do what they want, to be attracted to all these different nuclei equally. And because they're so satisfied, that makes it very hard to break it or change it. It makes a diamond hard. Okay, well, with regret, due to the time limitation, I'm going to move now from chemistry, where there were many, many beautiful examples, to a current frontier of understanding, or maybe misunderstanding, but I hope understanding the quantum beauty of unification. So here's a dodecahedron, which I introduced before, or Plato introduced originally. It's perhaps most familiar as a calendar, because it's very convenient. It has 12 sides that are nice and equal, so you can fit the same size month on each one. It sits very nice and is fascinating to look at. Okay, so that's the dodecahedron. It's becoming our friend. And so if we saw this on the internet, we'd know what it is. We know what it's meant to be. Look, it has 12 pentagons, 12 regular pentagons, partially connected. What this is meant to be is something you fold up and make into a dodecahedron, obviously. Right? Okay, but suppose some evil spirit erased part of it, made it harder to recognize. Now, well, most people who hadn't thought about dodecahedra and hadn't heard this lecture wouldn't know what to do with this. What the heck could that mean? What is it meant to be? But if you've studied regular solids and dodecahedra, are familiar with that idea, you might say, well, it's very special that we have pentagons, that they're connected in this particular way. What this is meant to be is a dodecahedron, but somebody's erased part of it. Okay, so keep that in mind. And now we discuss the standard model of particle physics, which describes an enormous wealth of facts, experimental hard realities about the physical world in a very compact set of equations. I will not remotely be able to do justice to what these equations are or their details, But I hope you'll trust me that, and there are physicists in the audience who can call me on this if they object, and I'll argue with them, but almost everything we know about physics is encoded honestly in this one slide, if you know how to decode it. And the decoding doesn't take putting in numbers or fudge factors or anything, but just spelling out the logic of what are called gauge symmetries, symmetries that generalize the symmetries that were discovered in Maxwell's equations, and in another Cambridge guy, Dirac's equation for these guys. These are the quarks, the leptons, neutrino and electron, 3 different colors of quarks. And you have transformations of the equations that are symmetries that change each of these kinds of quarks in this group into each of the other ones, and each of the leptons here into other ones, and so forth. So although there are a lot of particles that go into this description of physics, in some sense, most of them are the same particle. They are related by symmetry, one to the other, so they shouldn't be thought of as separate, independent elements of existence that you have to postulate. If you have one, you have to have them all, because the symmetry tells you that they transform one into the other, and the equations have to stay the same. So if the equations are going to be the same, the thing has to transform into something, so the something has to exist. So this is very powerful, very compact. It would be difficult, as I said, to exaggerate its precision, its power, and its beauty when you spell it out. But we're not satisfied. Just because this is so close to nature's last word, experimentalists have been trying to get beyond this to find phenomena that aren't included in the Standard Model, and win Nobel Prizes for themselves for the last 40 years without success. Very hard. We're spending a lot of money at accelerators and so on. Without success, so it really works. But it's not as beautiful as it could be. We're not satisfied because it has 3 fundamental forces in it: the strong, weak, and electromagnetic interactions. Gravity is another force, which we'll come back to, but even here we have 3 fundamental forces. So that's more than one. We'd like to have one unifying force that really underlies everything in a coherent description of nature. And also, we have 6 fundamental materials. I said these guys within the parentheses are all related to each other, so they should be thought of as really the same thing with different perspectives. But even allowing that, they fall into 6 unrelated bits. So we'd like to do better. It's as if we've been presented with this partial realization of a dodecahedron that's had something erased. All right? So knowing the mathematics of symmetry, then, just as if we know the mathematics of symmetry, we can figure out a dodecahedron. Here we can see if there are bigger structures that can be completed and unify all this. And of course, I wouldn't be telling you this if it didn't work. If you make a bigger symmetry, postulate a bigger symmetry with the equations, you have to expand the equations a bit, include phenomena that haven't been discovered yet, as Maxwell did, but as the reward for that, all the particles get related to one another. All the forces are different aspects of the same force. So we have just one material and one force. Really nice. But there seems to be a flaw when you first examine this idea. If we're going to have symmetry between the different interactions as observed, they have to have the same strengths, but as observed, they don't. The strong interaction really is stronger than the other interactions. So if we plot this way, so the strength of interaction points down, which you'll see in a minute why I did that, Strong is at the bottom. Weak, the so-called weak force, is actually stronger than electromagnetism once it turns on inside a nucleus. So this is the order of the three forces. In any case, they're definitely not equal. Too bad. Fortunately, however, one of the great lessons of the last part of the 20th century is that what we ordinarily perceive as empty space is, in fact, in our fundamental description of nature, far from empty. It's as if we're fish that have suddenly learned that they're immersed in a medium, water, that they've taken for granted until now. But as you think about it more, you find you can get a better description of nature by recognizing that you're in a medium that has its own properties. This is a picture of the deep structure of reality. This is what your eyes would see if they could have resolution in time of 10 to the minus 24th seconds and resolution in space of 10 to the minus 14th centimeters. So really, really small and really, really fast. But for your convenience in viewing, I've blown it up. These are based on hard calculations. These are fluctuations in the energy in gluon fields in our theory of quarks and gluons. That theory and these calculations are part of a successful account for how protons are made out of quarks and gluons, their mass, the mass and properties of many other related particles. So it's as certain as anything can be in science that this is a correct description of nature and what's going on at those short distances. So we live in a medium. It's a medium that's cloudy, turbulent, if you thought of it as water. It distorts our vision. And that's a good thing, because our vision seem to be spoiling this idea of unification. We seem to see things not being equal. But we have to correct. We have to strip away the effect of the medium to see the more basic interactions and see if they could be unified. So we can do that with the stroke of a pen. Although the experiments are very difficult, the LHC will basically cover the size of this circle at the cost of 10 billion euros, and then it gets really hard. But theoretically, there's no problem calculating what happens at much shorter distances, making corrections. So this is how the strength of the interaction evolves as you go to shorter distances or equivalently larger energies. And now we can see if it unifies with the other interactions. And here's what happens with the weak interaction. And you see they cross, so they do unify at short distances. Now, two lines do tend to meet in a point, so this perhaps is not as impressive as it could be. Well, things could have gone wrong, to be fair. They could have diverged, or they could have met too soon, which would lead to phenomena that aren't observed. But still, two lines do tend to meet in a point. So, fortunately, we have a third interaction to bring in, and so we can get a much more impressive test. I should say that it's the width of these lines tells you about the theoretical and experimental uncertainties in the numbers. So here it comes, the crucial test of unification. Does the third line meet? Don't. Almost, but not quite. Now, if we listen to a famous philosopher, not from Cambridge, I think, Karl Popper, who told us that the goal of science was to produce falsifiable theories, we could be happy at this point. We produced a theory that's not only falsifiable, but even false. What could be better than that? But of course, that's not the way we think about it. If we have a beautiful idea that seems promising, such ideas are precious. We shouldn't give up too easily. And in the spirit of youth and arrogance, maybe we just haven't been bold enough. So here's what we've done. We've united the description of the different kinds of matter, including electrons and quarks, which seem to have very different properties, but in these unified theories, they're just things that can transform into each other under symmetries of the equations. And similarly, photons and gluons are unified, so they're different aspects of the same thing. We were left with one force, one kind of matter. That's still two things. And two is more than one. So the obvious question is, can we connect those two, forces and particles? They seem to be very different, as different as apples and oranges. Can we do this? Well, for a long time that was thought to be difficult or impossible. Well, impossible. But in the 1970s, two physicists, mainly Wess and Zumino, developed another powerful unifying idea which does allow us to devise equations that are symmetric between these two different, very different kinds of things, the electrons and quarks on one hand and photons and gluons on the other. This is called supersymmetry. The central idea of supersymmetry is that there's a new dimension of space-time, but it's not a dimension you can move around in easily and retain your identity. What happens is if you move in this quantum dimension, is not that you've changed your position with respect to other people, but you've changed what kind of particle you are. So the matter kinds of particles turn into force kind of particles, the force kind of particles turn into matter kinds of particles, or more technically, fermions and bosons transform one into the other when they move into superspace. So we have the ordinary plane of existence and then the superworld where electrons turn into selectrons, a spin zero version of electrons. Gluons turn into gluinos, a sort of matter version of gluons, and so forth. And now, by flipping these two planes, if the equations of the world are supersymmetric, we'll get different equations where the particles have changed one into the other, but those equations will have the same content. So we're going in the direction that Maxwell suggested, or his successors, that's been so fruitful. Even one more step. And if you do that, now there's a way to change apples into oranges. And once you learn how to do it, it's really fun. You flip over the quantum dimension, and it's hard to stop, but okay. So there's a cost to this. We have to introduce this new plane, new world. We have to make bigger equations that make use of that extra space and make them symmetric. So there are extra particles now, new ingredients of the world, and like the gluons that I showed you, they also fluctuate in space. They make what are called virtual particles. So they have fluctuating energy in space too. Everybody does, according to quantum mechanics. And so when we calculate how empty space, what we were designed, or I guess according to Darwin, evolved to regard as nothingness, as emptiness, because it would not do us much good to be able to see these fluctuations. It wouldn't help us select desirable mates or find good fruit or anything like that. But in our equations, we have to make those corrections to see what's really going on at very short distances. And so they make new corrections. I have to redo that calculation. And here it comes. If you put in the supersymmetry, put in those additional corrections, now they really do come together and unify. And by the way, if you complete the equations properly, they don't ununify again, they stick together. And as a special unexpected bonus, gravity, which started out horrendously weaker than the other forces, so on this plot would be way outside the known universe. So although I went to great effort to plot it up there, you can't see it. So it's not a factor of 10, but 40 factors of 10 weaker than the strong force. So you have to multiply by 10 and then 10 again to the atmosphere, the moon, the solar system, way outside the known universe. But it comes roaring in the calculation, and then here you see it manages also to unify with the other interactions pretty much. So that's the way this vision of the world and these series of successes, the really carrying out the dreams of Plato and Pythagoras and getting inspiration from Newton and Maxwell have led us today. Can we test it? I hope you'll agree this is all very pretty and tantalizing. Well, if Susie's new particles that we're using to make fluctuations are going to do this job, they can't be too heavy. And it turns out that the new Large Hadron Collider, a fantastic undertaking at CERN near Geneva, if they exist and are light enough to do this job, they'll be created and detected. So there's going to be a trial by fire. Either these ideas will go up in smoke, or at this fantastic machine, 18 miles or 27 kilometers around. Of course, you don't really see this red line on the Earth. It's underground. It's very hard work keeping it going. This all has to be kept at 2 degrees above absolute zero. It's 27 kilometers of very powerful magnets, like you would be put into if you were getting an MRI image done at a hospital. But they have to be very precisely aligned for 27 kilometers solid. All kept cold so that they can be superconducting and be energetically efficient. It's the coldest extended region on Earth, in the universe, as far as we know. It's even colder than outer space, which has the 3-degree microwave background radiation. This is 2 degrees. It's colder. Very hard work. You can see the people involved get exhausted. But and this is what the detectors look like that will try to unravel what happens when protons collide at extremely high energies. This is our civilization's answer to the pyramids of Egypt, but much better because it's not just sandstone. It's very advanced electronics that's actually there for a purpose other than vanity. And anyway, very impressive. Whoops, I see I repeated. There'll be a trial by fire. Do they show up? If not, we're done. And Karl Popper will be very happy. We've falsified. But another possibility that might happen is that when we analyze the pictures of what's been produced that these detectors will give us, we'll find out that, well, most of this stuff is stuff that's already incorporated in the standard model. The particles are ones we've seen before, and the interactions are one we've seen before. But once in a while, maybe once in a billion or once in a trillion events, there'll be something else that does not conform to the standard model. Another kind of particle that you have to analyze to find it. It's very hard, but okay. But properly analyzed, this is speaking to us, saying, here I am. I'm a supersymmetric particle. Here I am. I'm another one. And then these visions of unification will be taken to a new level of truth and vindication. So we've heard a siren song of symmetry and worked hard to swim ashore to get a closer look at what the sirens are promising. We'll soon see whether nature's been subtle or malicious. Here's a picture of it. I've left behind the safety of the standard model, gone into the unknown icy waters of speculation and supersymmetry, led on by the siren song of symmetry. And soon we'll know. It's a very exciting time for us. Thank you very much for your attention.
I got a distinct sense of nostalgia about that because I worked out it was precisely 50 years ago, probably this month actually, that as a rather earnest teenager at Leeds Grammar School I constructed all those regular polyhedra and the 2-1 with concave surfaces out of balsa wood. And I did so because I was so fascinated by the mathematics. And it's that sense of fascination that Professor Wilczek has communicated so beautifully tonight. The notion of the beauty of soot is new to me, I have to say, but as a fantastic exposition of the power of theory, I think that was wonderful. A theory of everything, clearly, and a wonderful account of when the real meets the ideal. Thank you very much indeed.